Okay, let's get started with Module 2 for CIS 140NA. We're going to cover 4 chapters this week, chapters 5, 7, 8, and 11. There's actually not too much to these chapters, so this lecture won't take too long. Starting with chapter 5 and defining your global configuration files and folders. Wireshark consists of 2 types of configuration, your personal and your global. You can find the locations for them under Help About Wireshark folders. You can set a variety of global configurations that will affect every setting in your system. For example, the C filters have the list of the default capture filters that are available to you when you open Wireshark. The D filters file has the default display filters. The file called color filters has all the default coloring rules. ManuF has all the MAC addresses that it has in store. The default port list under services, and the default MIB modules to load. Most of these files are either copied on your personal configuration folder, a profile folder, or can be copied to another system. The issue lies in any reference to a file that may not exist in the destination system. During an update of Wireshark, the settings will not be removed unless you specify during the process. So these text files can all be updated by you manually because they're all text files, and you are able to copy them to other systems as you move from system to system and you get familiar and you want a specific setup for Wireshark. Mainly, when customizing your user interface, you would go under Edit and Preferences. You could change things like the maximum list entries, any pane configurations, capture preferences. You could enable or disable to automatically scroll in real time. So if you're, for example, if you're capturing a lot of data, you don't want this on. You would want to turn that off. Automatically resolve IP and MAC addresses. Again, something that you may want to turn off when you want to be as stealthy as possible and you don't want your system to send packets out on the network and thus adding more traffic on your host. You can also plot IP addresses in a world map. If you want to see more, you can look at page 168 in the big book. There are also settings to resolve port numbers and SNMP information, along with any filter expressions that you might want to have preset. Again, Wireshark already is able to automatically resolve IP addresses based on what's in the menu file. You can modify these in order to meet your needs. Wireshark is customizable to a large extent to meet whatever situation you're going to work with. I highly recommend spending some time looking into those preferences and see how deeper can you get into the traffic you are listening to by making adjustments to the program. Don't forget that you can always right-click on options available when looking at a packet. A lot of the options that are very specific to a specific conversation or to a specific packet are available quickly by right-clicking on it and going to things like protocol preferences. Chapter 7 is all about the time values and the interpret summaries. So while chapter 5 is you can make major changes to the program to meet the needs of whatever situation you're working on, and as you develop what you want to have handy in Wireshark, you can set that globally. This will focus more on time, because time will be important if, for example, we need to submit our packet capture to court because of a trial. When troubleshooting slow network communications, the time column will be the place to focus. High latency, access errors, excessive packets, and other issues will appear as large gaps in time between the request and acknowledgement. Wireshark gets timestamps from the libpcap library, which in turn it gets from the OS kernel. The pcap file format consists of a record header for each packet, a 4-byte value defining the packet in seconds from epoch, or January 1, 1970, 000 UTC. This will be followed by another 4-byte value defining the microseconds since that point in time. In order to make changes to time, you would go under View and then Time Display Format. Ideally, before you start your capture, you want to ensure that your operating system is already in sync with network time protocol before starting. There are a series of issues and delays that may happen. The big thing that I do want to stress is using native NIC cards are better because they don't have the problem of timing issues. You might get a delay. And remember, with packet capture, we need to capture everything as perfect as possible. We really don't want to deal with delays. And the more newer USB NICs may not have that problem. But for most USB NICs, they will have a timing issue where you'll miss packets, and if you miss packets, your capture won't be complete. Within this time display format, you have quite the number of settings, like the day and time, setting since epoch, second since beginning of capture, since previous capture packet, previously display packet, and UTC. You will see this term used a lot, the delta time. This is seconds since previous captured packet. So if you have 2 packets, delta time on packet 2 is determined by when packet 1 happened. If you have 100 packets, packet number 59 time will be based off of packet 0. This is great to use when figuring out delays in communication. You have the beginning of the communication, let's make that delta time. And then we figure out how long the delay was. The great thing about delta is it doesn't actually have to apply to the very first packet. You can determine which packet will be the first packet and apply delta time to that. There are a number of hands-on examples that you can use to see this in action. to see communication happening and figure out those delays. So again, to isolate slow performance caused by high latency, expand the frame, right-click on time delta from previous displayed frame and apply it as a column. This new column can show the large delays between display packets, allowing us to look sequentially at the traffic surrounding those gaps to see what led up to the problem. You can have a number of columns with time, like absolute date and time, the delta time displayed, relative, and time as set in the time display format. You can set and unset time reference with Control T. That is also useful. And that will make whatever packet you are selecting to set the time reference to 0. And then everything else will go after that, making that the delta time. All captured packets display a marked packet in the trace file and are visible from summary window under the statistics capture file properties. Again, a lot of the stuff that we'll do will be determined by time. So being able to manipulate time easily, like for example, finding out the start of a conversation within a large capture and saying this is going to be the start. So let's set delta time here, and then looking at the delay or looking at the conversation from there will be essential in all the labs that you'll be doing later on. That should actually say chapter 8. I'm not sure why it says chapter 7. So chapter 8 is about basic trace file statistics. There's a whole section on graphing that we'll get to as well. Wireshark is awesome in providing you statistics. This chapter will give you the basics of that. To begin, statistics protocol hierarchy will tell you all the protocols that are happening or that happened in the capture, along with how many packets were used for that specific protocol, their percentage, the percentage bytes, along with bits per second, end packets, and bytes, a whole lot of information that is a treasure trove when doing analysis. That window under statistics protocol hierarchy will display you things like the packet count, bytes count, percentages, and more. The protocols and applications are categorized according to their protocol layer. So this is where that reminder of the OSI model comes very much in use. If you disable allow subdissectors to reassemble TCP streams, you'll actually get even more information that's already available in the protocol hierarchy statistics. Again, this place, the protocol hierarchy, is useful and important when characterizing traffic to and from a host that you suspect may be compromised. You could look for unusual ports or applications like IRC, TFTP, RPC, etc., or just anything that you don't recognize. Under statistics conversations, you'll be able to see the most chattiest systems in the capture. You'll be able to see all conversations that are occurring from ARP, IMCP, or ICMP, FTP, and so on. Conversations can be pairs of hosts communicating while an endpoint is a single side of the conversation. Broadcast and multicast to host are also listed as conversations, even though there is no broadcast or multicast host. You can sort them by various columns to see what conversations are the most active based on packets, bytes, bits per second, or total duration of conversation. Though there is only one Ethernet conversation, there are several TCP, IP, and UDP. And again, you can sort them under the conversations. You can also see statistics by endpoints if you want it as well. In order to see endpoints on a world map, you'll need GeoIP, which is something that we'll explain later, but you can map them, which is pretty crazy. You can map them to see what's happening where. So this is a picture of the protocol hierarchy. As you can see, we have Ethernet, we have IPv4, we have, well, we see that TCP connections were a little over half, actually a little under half, 48%. And then you can dig down to see, SMB was 0.19. We see that UDP is 53%, and that TFTP was the biggest chunk of that. It's pretty awesome how much information this gives you. Like I said, packet lengths are important in looking at the statistics. If we have a file that's 500,000 bytes to send, how many packets will it take to send on a standard network of Ethernet 802.3? Well, we have 1518 total bytes and 15,000 MTU bytes. We have to count for the overhead, so that'll be less. We got 1460 to work with. It'll take about 343 packets of data to send that information. Along with all the headers, that's how much we're looking at. We're looking at a total of 519,000 bytes. The data and the overhead. This math is important because when we look at the statistics, we need to keep in mind what we're looking at. In this picture, the MAC IP TCP header overhead shown does not factor in the unseen overhead elements, such as the preamble and interpacket gap if required. When using a standard Ethernet 2 header as shown above, you are left with 1460 bytes able to handle the segmented data. A file transfer application should be examined with focus to their packet lengths. If you are having trouble with file transfer, it could be application is transferring files smaller than the MTU. A device along the path is limiting the MTU size, and application was not developed to take advantage of MTU sizes. With file transfer, it is best that the packets are bigger. Less packets on the wire, more data being transferred, that's good. Not so much of going smaller packets. That causes more problems. Just like I said that. Yeah, so like email does send more packets and smaller. Databases do this too. So those are fine. If you see a lot of little database packets, that's normal. But if you started seeing large database packets, that would be a weird anomaly. You want to hunt down those guilty ports that are causing any issues. Some ways to hunt for devices that are causing issues with this would be by searching which packets are creating this type of packet, the ICMP type 3 code 4. To list the usage of IP protocols, that would be under IP protocol types. Only packets that have a UDP or a TCP header will be counted. You are able to use any display filters here. the conversation or endpoint window might actually be more beneficial to you, but it is there. It is an option that you could use that to see to see streams and filter them as needed. Like I said, there's a whole section, a whole chapter dedicated to graphing, but as an initial, you could go under statistics and see flow graphs. Those flow graphs can be created based on all traffic, filtered traffic, or just the TCP flows. It is a very quick and easy tool to see web browsing issues. For example, slow reconnections are usually a problem because of multiple redirections, and you will see those redirections in that flow graph. You'll see a lot of 404 errors. A lot of those things come to light when looking at the flow graph. Wireshark already has built-in tools for specific protocols. For example, HTTP. Under statistics, you will find an entire section dedicated to HTTP. You can see a packet counter information that breaks down by the codes. These codes you should be familiar with. For example, anything in the 100 is all informational. Anything in the 200 are all successes. 300s are all redirection. 400 is the client error. 500 is the server. Seeing those statistics, seeing the packet counters by these codes will help you quickly see, is it a problem at the client's end? Is it a problem at the server's end? WLAN has all the statistics for that, like the BSS IDs, the channels, packet percentages, and so on, that we'll dig into later in another module. But know that you can get the WLAN statistics right there in an easy to reach place. Lastly, for this week, circling back to profiles, because again, profiles are going to become very useful when working on various issues. For example, what you do with wireless will be different with what you do with wire, which will be different what you do with like VoIP or web browsing or email. So having profiles for different issues becomes a very useful tool to quickly prepare Wireshark to look into specific types of conversations. Like a user profile on an OS, these make life much more efficient. When you create a new profile, it'll have a directory with that name. The number of files contained in the profiles directory will depend on what you add. The great thing is you can copy these out, like just drag and drop these folders out to other Wireshark installs if you are moving around from machine to machine. When you restart Wireshark, whatever the last profile was used will be the one automatically loaded. There are some examples in the book that I suggest looking at, but honestly, it is ideal as network analysis to have various profiles for various situations that you will be working with. There is one that you'll actually use for some of the labs in this chapter and going forward for a couple chapters. But I suggest as you get more into network analysis to create these profiles. And you'll see, again, you'll see the same folders that we talked about, the same files that we talked about, the C filters for anything capture, the D filters for all display, the color filters to set certain colors to certain things within a packet, any specific preferences that you may have, and filter expressions. In the notes, in my lecture notes, I have given you some examples. For example, a troubleshooting profile could have this under the C filter. So this, you would change this to be your MAC address that you're using. That way, when it filters data captured in the wire, it won't get yours. Your display filter could have these items already within it. Your color filters could have these. And your preferences could have these already within those files. So when you load up this profile, all these things will take effect. Let's say a corporate profile. You could use similar things above and make adjustments based on what key protocols and ports are used at that location. Your wireless profile will definitely be different from your wired. So you can make various rules that, for example, will tell you, hey, there's a weak signal happening, or there's disassociation frames that are occurring if somebody's walking around with a Ponagachi. A VoIP profile would be different from the ones above because of the traffic that we're looking at. So things like status codes could be set as display filters, and also color rules to see them quickly. And security profile, if we're looking at a breach, if we're looking at some sort of security issue, that profile would look different from a troubleshooting profile like the ones listed before. Wireshark is versatile in allowing you to modify it for various situations. And I cannot stress highly enough using profiles. It will make your analysis smoother. It will make your life easier because you'll have things preset for issues, and will help you in digging through packets to find the information you're looking for to troubleshoot the issue, to get to the bottom of the problem. So like I said, for the next couple of weeks, this week through week 4, you should be using the profile that comes from this zip file that you can download and add. You can verify that your settings take effect with using this specific packet capture, this trace file. If you go through these settings and you see that it all works, frame 8 should say validation disabled. It should list bytes in flight under timestamps. You should see new timestamps included. So this is your check that after applying the new profile, everything looks correct. You'll use that for your assignments for the next 3 weeks. Yes, weeks 2, week 3, and week 4. So you'll import that profile, check everything, see the new buttons that are available, and make your own as you go. You have some questions to answer as well with other files. This definitely requires having Wireshark and not using CloudShark. So if you need Google Cloud credit in order to install Wireshark and run it in the cloud, let me know. I have plenty of codes to issue out to all students, so you can make your own cloud instance. And as always, if you have any questions, please feel free to contact me on Discord.